Welcome back to Physics 192. I'm Gerard Blanchard. This time, we're going to start coverage of our final topic in Physics 192, and that is nuclear physics. As far as we know today, there are four fundamental forces at work in the universe. Those are the gravitational force, the electrical force, the strong nuclear force, and the weak nuclear force. We've already covered the gravitational force and the electrical force. So to wrap up general physics, we're going to talk about the strong nuclear force and the weak nuclear force. These forces are responsible for the identity of the elements themselves. Protons and neutrons are bound together in the nucleus by the strong nuclear force. The strong nuclear force is an attractive force between all nucleons, where by nucleons I mean protons and neutrons. The attractive, strong nuclear force is stronger than the repulsive electric force at distances of less than approximately 3 × 10 to the minus 15 meters. That's why nuclei are so small, because they have to be that small in order for the strong nuclear force to hold them together. Electrons do not feel the strong nuclear force. That's why the electrons are not bound in the nucleus. That's why they orbit the nucleus under the influence of the electrical force. So protons and neutrons feel the strong nuclear force, but electrons only feel the electrical force. So the protons and neutrons are bound tightly together in the nucleus, while the electrons stay at a greater distance. Since the strong nuclear force is an attractive force, work, or energy, is needed to separate nucleons against the effect of the strong nuclear force. This work we call the binding energy. The work that would be necessary to separate the nucleons is called the binding energy. And the binding energy is sufficiently large that it significantly changes the mass of nuclei by about 0.1% in accordance with the energy-mass relationship, Einstein's energy-mass relationship of energy is equal to mass times the speed of light squared. So we're going to be using that equation a lot in this section. Energy is equal to mass times the speed of light squared. As an example, let's consider carbon-12. And the way that we write carbon-12 is with a superscript 12 in front of the letter C that represents carbon. So it would be superscript 12C, but we read it as carbon-12. 12 is the mass number of carbon-12, and the mass number is the total number of protons and neutrons in the nucleus. So there are a total of 6 protons. We get that from knowing that it's carbon. Carbon is element 6, so there are 6 protons and then 6 neutrons in carbon-12 for a total of 12 nucleons. So to find the binding energy of carbon-12, we would break up the carbon into its component protons and neutrons. And we would write that in a reaction equation as follows. Carbon-12 becomes 6 protons plus 6 neutrons. So we start with the carbon-12 and we break it apart into its component protons and neutrons. The mass of a carbon-12 nucleus is 1.992 times 10 to the minus 26 kilograms. Very, very small. 1.992 times 10 to the minus 26 kilograms. Now I got that from a table of the isotopes. We'll talk a little bit more about that later. And that becomes 6 protons. So the mass of the 6 individual protons would be 6 times 1.673 times 10 to the minus 27 kilograms. And once again, I got that mass, the mass of a proton, from a table of the isotopes. and 6 neutrons, the mass of a neutron is slightly larger than the mass of a proton, so that becomes 6 times 1.675 times 10 to the minus 27 kilograms. If we calculate the right-hand side of that equation, that becomes 2.008 times 10 to the minus 26 kilograms. So 1.992 times 10 to the minus 26 kilograms becomes 2.008 times 10 to the minus 26 kilograms. So by separating the protons and neutrons from the carbon-12 nucleus, we've actually increased their total mass. How did we do that? We did that by giving them energy in accordance with the equation, energy is equal to mass times the speed of light squared. So we had to make up the difference in the mass by giving the nucleus energy. Let's calculate the amount of energy that we had to give. Let's calculate the energy in the initial carbon-12 nucleus. That would be 1.992 times 10 to the minus 26 kilograms times the speed of light, which is 2.998 times 10 to the 8 meters per second. I got that out of the table in the back of your book. And we square the speed of light. And that becomes 2.008 times 10 to the minus 26 kilograms times the speed of light squared, or the initial energy of the carbon-12 nucleus, 1.790 times 10 to the minus 9 joules, becomes 1.805 times 10 to the minus 9 joules. So we had to make up the energy difference. And that energy difference is the binding energy, the amount of energy that we had to give, specifically 1.805 times 10 to the minus 9 joules minus 1.79 times 10 to the minus joules, or 1.5 times 10 to the minus 11 joules, is the binding energy. Another way of looking at this is the mass defect. The mass defect is the amount of mass that the protons and neutrons have to gain in order to be separated. And that is 2.008 times 10 to the minus 26 kilograms. That's the mass of the loose protons and neutrons, minus 1.992 times 10 to the minus 26 kilograms. That's the total mass that they had in the nucleus. And that's a difference of 1.6 times 10 to the minus 28 kilograms. So a carbon-12 nucleus has a mass defect of 1.6 times 10 to the minus 28 kilograms. Or in other words, it has to gain that much mass in order to be separated into its component parts. An equivalent way of looking at this is to say that the carbon-12 nucleus has to gain 1.5 times 10 to the minus 11 joules in order to be separated into its component parts. Now, no one really uses kilograms and joules when talking about nuclei. Those units are just too big. As you saw, we're talking about masses of 10 to the minus 26 kilograms, or energies of 10 to the minus 10 joules. So for convenience sake, we're not going to use basic metric units when we're talking about nuclei. We're going to use other, more conveniently sized units. For mass, we're going to use the atomic mass unit, and that's symbolized with simply a lowercase u. And 1 u is equal to 1.660539 times 10 to the minus 27 kilograms. An atomic mass unit is actually 1/12 of the mass of a nucleus of carbon-12. So carbon-12 is the standard for deriving the atomic mass unit. So one atomic mass unit is 1.660539, and we're going to need all of those digits, times 10 to the minus 27 kilograms. For energy, we're going to use a unit called the mega electron volt. You may have encountered electron volt before in chemistry, so you know that atomic energies are on the order of electron volts or tens of electron volts, while nuclear energies are on the order of mega electron volts, so 1,000,000 or 100,000 times larger. 1 mega electron volt is equal to 1.602177 times 10 to the minus 13 joules. So you can see that these two units are comparable with the numbers that we got for carbon-12. Now, 1 atomic mass unit times c squared, we can work out and figure out that that's equal to 931.494 mega electron volts. Or we can say that the speed of light squared is equal to 931.494 mega electron volts per atomic mass unit. So when you write c squared, you won't have to write 3 times 10 to the 8 meters per second squared. You can just write that the speed of light squared is equal to 931.494 mega electron volts per atomic mass unit. So with these units, let's repeat what we did for carbon-12. Carbon-12 becomes 6 protons plus 6 neutrons. The mass of carbon-12, of a carbon-12 nucleus in atomic mass units, is 11.9967 atomic mass units. Now I just said that the mass of carbon-12 was 12 atomic mass units. That is the mass of the carbon-12 atom. In this exercise, I'm just using the mass of the carbon-12 nucleus. So I had to subtract off the mass of 12 electrons. So in atomic mass units, the mass of a carbon-12 nucleus is 11.9967 atomic mass units. And that becomes 6 proton masses, where a proton mass is 1.0073 atomic mass units, and 6 neutrons, where that is 6 times 1.0087 atomic mass units. So 11.9967 atomic mass units becomes 12.0960 atomic mass units. So the mass defect is 12.0960 atomic mass units minus 11.9967 atomic mass units, or 0.0993 atomic mass units. So you see, we're not having to write times 10 to the minus 26 here. Converting that into energy, on the left-hand side, we have 11.9967 atomic mass units times c squared, which is 931.494 mega electron volts per atomic mass unit, or 11,174.9 mega electron volts, becomes 12.0960 atomic mass units times 931.494 mega electron volts per atomic mass unit, and that is 11,267.4 mega electron volts. So the binding energy, which is the difference of those two energies, is 11,276.4 mega electron volts minus 11,174.9 mega electron volts, or 92.5 mega electron volts. Now, I would like you to work an exercise. Find the binding energy of a deuterium nucleus. And a deuterium nucleus is a hydrogen-2 nucleus, 1 proton, 1 neutron. And find the binding energy in mega electron volts. The mass of a deuterium nucleus is 2.0136 atomic mass units. The mass of a proton, just for your reference, is 1.0073 atomic mass units, and the mass of a neutron is 1.0087 atomic mass units. Now, the mass of the deuterium nucleus that I gave you is in fact the mass of the nucleus. I've already subtracted off the mass of any electrons. So 2.0136 atomic mass units is the mass of the deuterium nucleus alone. So you don't have to worry about electrons. We'll talk about dealing with electrons shortly, but for now, you can use that number, 2.0136 atomic mass units, because that is the mass of the deuterium nucleus alone. Our reaction is hydrogen 2, which is our deuterium nucleus, which is hydrogen is element 1, so that's 1 proton. So it becomes 1 proton and plus 1 neutron. So that's what deuterium is. It's a proton and a neutron bound together by the strong nuclear force. The mass of the deuterium nucleus you were given is 2.0136 atomic mass units, and that becomes 1 times the mass of a proton, 1.0073 atomic mass units, plus 1 times the mass of a neutron, 1.0087 atomic mass units. So that is our mass equation. Now, let's multiply by c squared. Let's multiply the mass times c squared, times the speed of light squared, to get the energy, where for c squared, let me go ahead and write out the mass again. I have 2.0136 atomic mass units times c squared in the form of 931.494 MeV per c squared. Now, just point out, since we're not using basic metric units, oops, I made a mistake here, sorry. That is not MeV per c squared, that's MeV per atomic mass unit. Okay, since I'm not using basic metric units, I must explicitly write out my units so that we know what units the numbers are in. We can't assume that they're in basic metric units anymore because we've changed units for our convenience. So this is mega electron volts per atomic mass unit. I have atomic mass unit divided by atomic mass unit. Those atomic mass units will cancel out. So this right here, 2.0136 times 931.494 MeV is 2.0136 times 931.494. 2.0136 times 931.494. That gives us an energy, and I'm going to, let's see, 1, 2, 3, 4, 5. I'm going to keep 5 significant figures. We have to keep a good number of significant figures because we're going to be doing some subtracting, and the bulk of the numbers will subtract out. So our differences are going to be in our, there's going to be several significant figures down in our numbers. So I'm going to keep, I'll keep 1, 2, 3, 4, 5 significant figures, which would be 1,875.7, 1,875.7 mega electron volts, because that's the only unit we have left here. Our atomic mass units have canceled out. and we're left with mega electron volts. And that becomes our total mass over here, which is 1.0073 plus 1.0087 atomic mass units. 1.0073, 1.0087 atomic mass units times 931.494 mega electron volts per atomic mass unit. Our atomic mass units cancel out. And what I did here is I just factored out the atomic mass unit from both of those numbers. So I have atomic mass units here divided by atomic mass units. And those cancel out. So let's see what we have here. We have the quantity 1.0073 plus 1.0087. So we have that quantity times 931.494, and that gives us 1,877, 1877.9 MeV. So the deuterium starts out with 1,875.7 mega electron volts, and we have to give it the difference to bring it up to 1,877.9 mega electron volts in order to split it up into its component proton and neutron. So the binding energy is this number minus this number. So it would be 1877.9 MeV minus 1875.7 MeV. And that difference is 1877.9 minus 1875.7, and that is 2.2 mega electron volts. So that means that in order to split the deuterium into its component nucleons, we had to give it somehow 2.2 mega electron volts of energy. And you can see what I was talking about here, where we have two very similar numbers that we're subtracting. So even though we started out with 1, 2, 3, 4, 5 significant figures, when we did the subtraction, we were only left with 2 significant figures. So that's why we have to initially keep so many significant figures, and that's why I gave you these numbers to such precision. Let's work another example. Find the binding energy of the oxygen-16 nucleus. A table of isotopes informs you that the mass of an oxygen-16 atom is 15.9949 atomic mass units. Now, where can you find a table of isotopes? Your general physics book will contain a table of isotopes. You can also find them online in many, many places. So a table of isotopes will tell you that the mass of an oxygen-16 atom is 15.9949 atomic mass units. Now, a couple of things. The atomic number of oxygen is 8. That means that oxygen is element 8. That means it contains 8 protons. So of the 16 nucleons in the oxygen-16 nucleus, 8 of them are protons and the other 8 are neutrons. And another thing is, since the table of isotopes tend to give us the mass of the atom, which is the nucleus plus its electrons, we're going to have to subtract off from 15.9949 atomic mass units the mass of 8 electrons. So, since an oxygen atom contains 8 protons, it'll also contain 8 electrons. When we're doing nuclear physics, we have to subtract off the mass of the electrons. We're just dealing with the nuclei. And so the mass of an electron is 0.000549 atomic mass units. So once again, the mass of an electron is 0.000549 atomic mass units. And you can refer to your notes from the last exercise to get the mass of a proton and the mass of a neutron. So please calculate the binding energy of an oxygen-16 nucleus. We have oxygen-16 becoming 8 protons plus 8 neutrons. The mass of the oxygen-16 nucleus is 15.9949 atomic mass units, which is what we got from our table, minus the mass of 8 electrons. So I have to subtract off 8 times the mass of an electron, 0.000549 atomic mass units. So that is the mass of an oxygen atom minus the mass of 8 electrons. We've already stripped off those electrons. And that becomes 8 times the mass of a proton, the mass of a proton being 1.0073 atomic mass units, plus 8 times the mass of a neutron, and that is 1.0087 atomic mass units. Let's go ahead and do this subtraction and this addition to find the totals on each side. 15.9949 minus 8 times 0.000549 equals 15.99, let's see, how many significant figures? 15.9905. So I'll keep the same number of significant figures, or the same place of the significant figures as I have here. So it'd be 15.9905. So remember, when we subtract, we keep the same place as our least significant figure, and that would be this right here. So 15.9905. 9905, yeah. So we're okay there. 15.9905 is what we have on this side. And that becomes 8 times 1.0073 plus 8 times 1.0087. 16.128. And let's see. Okay, 16.128. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, same number of significant figures. And these are atomic mass units. Have to keep my atomic mass units. So 15.9905 atomic mass units of mass becomes 16.128 atomic mass units of mass. So we have to add mass in the form of energy to break apart this oxygen-16 into its component protons and neutrons. So let's calculate energy. We have 15.9905 atomic mass units times 931.494 MeV per atomic mass unit. Cancel all my units. And that becomes 16.128 atomic mass units times 931.494 MeV per atomic mass unit. Cancel out my units. And what is that? 15.9905 times 931.494. That is 14,895. And I guess I can have one more significant figure. 0.1. Excuse me. So it'd be 14,895.1 MeV becomes 16.128 times 931.494. That becomes 15,023.1 MeV. And so the binding energy is the difference, the amount of energy that we need to give the nucleus to go from here to here. And that would be 15,023.1 minus 14,895.1, and those are both MeV, mega electron volts. And so that would be 15,023.1 minus 14,895.1, and that would be 128.0 mega electron volts. So the binding energy of oxygen-16 is 128.0 mega electron volts. Let's work one more example. Using a mass spectrometer, the mass of a singly ionized uranium-238 ion is found to be 238.0502 atomic mass units. Find the binding energy of the uranium-238 nucleus. Now, why does it have to be ionized? A mass spectrometer only works on charged particles. So in order to find the mass of the uranium, we had to ionize it by taking away an electron. So it's a singly positively ionized uranium-238 ion. The atomic number of uranium is 92. Uranium is element 92. So the uranium nucleus contains 92 protons and however many neutrons it takes to make up 238. From that number, 238.0502 atomic mass units, we're going to have to subtract off the mass of some electrons. If it were a uranium atom, a neutral atom, it would have 92 electrons, but since this is a singly ionized ion, it only has 91 electrons. So that number, 238.0502 atomic mass units, is the mass of the uranium-238 nucleus plus the mass of 91 electrons. So you're going to have to subtract off the mass of 91 electrons. And then you're going to break up the uranium-238 nucleus into 92 protons plus, how many will that be? That'll be 146 neutrons. So 92 protons and 146 neutrons. Okay, so here's our reaction. We have uranium-238, a uranium-238 nucleus becomes 92 protons plus 146 neutrons. So we're breaking up this massive uranium-238 nucleus into 92 protons and 146 neutrons. The mass of a uranium-238 nucleus is the figure that we got, 238.0502 atomic mass units, minus the mass of 91 electrons, because that, when we measured this, the nucleus was carrying around 91 electrons with it. And the mass of an electron is 0.000549 atomic mass units. And that becomes 92 times the mass of a proton, 1.0073 atomic mass units, plus 146 times the mass of a neutron, 1.0087 atomic mass units. Okay, let's calculate the mass on either side. 238.0502 minus 91 times 0.000549 gives us 238.0002. So over here we have 238.0002 atomic mass units. And that becomes 92 times 1.0073 plus 146 times 1.0087, and that would be 239.9418 atomic mass units. Okay. And so this much mass becomes this much mass. So we had to add mass to break the uranium nucleus up. Let's convert that to energy to figure out how much energy we had to give it. 238.0002 times 931.494, that's atomic mass units, and this is mega electron volts per atomic mass unit, becomes 239.9418 atomic mass units times 931.494 mega electron volts per atomic mass unit. Cancel off our atomic mass units. And that tells us that, okay, 238.0002 times 931.494 becomes 221695, 221, put a comma, 695, and I only have 6 significant figures here, so I only keep 6 significant figures here, so that's 22169. Actually, I have to round that up, 696. If I'm going to stop here, mega electron volts becomes excuse me, 239.9418 times 931.494. So that becomes 223,504. I'm sorry, 223,504. 223,504 mega electron volts. So we have to get the nucleus from this energy to this energy. So we had to add 223,504 MeV minus 221,696 MeV. And so that difference is 223,504 minus 221,696 for a difference of 1,808 mega electron volts. So that's the amount of energy we would have to give to the uranium nucleus in order to split it apart into its component electrons and neutrons. So that is the binding energy of the uranium nucleus. So we've talked about the strong nuclear force and the binding energy of nuclei. Next time, we'll talk about the weak nuclear force. Until then, think physics.